Hello everyone. Welcome to this Applied Remote Sensing training on Introduction to NASA Snow and Ice Data Products and Applications. Part 1 today is going to be about overview of NASA Snow and Ice Data Products. I'm Amita Mehta from ARSET, and we have guest instructors today, Mr. Andy Barrett and Mr. Walter Meier from NSIDC, National Snow and Ice Data Center, and Mr. Ryan Theurer from Airborne Snow Observatory, or ASO. We'll start with a brief introduction to ARSET for those of you who are taking ARSET training for the first time. So ARSET provides accessible, relevant, and cost-free training on remote sensing satellites, sensors, methods, and tools. And it's part of NASA's capacity building program. ARSET trainings include a variety of applications of satellite data and are tailored to audiences with a variety of experience levels. The thematic areas on which ARSET trainings are focused on are listed here: agriculture, climate and resilience, disasters, ecological conservation, health and air quality, water resources, and wildland fires. ARSET trainings are mostly online, but there are also in-person trainings. They are live and instructor-led, or there are asynchronous and self-paced trainings available from ARSET websites that can be taken in your own time. They're cost-free, as I mentioned earlier. Most trainings are bilingual in the sense that the material is always available in Spanish. Sometimes the trainings are conducted in Spanish as well, and sometimes there are multilingual options such as French. We only use open source software and data and accommodate differing levels of expertise from introductory all the way to advanced level of background in remote sensing. We'll start with a brief overview of this training. It's Introduction to NASA Snow and Ice Data Products and Applications. So why do we want to learn about snow and ice products? And because frozen water in the Earth system is quite important, um, frozen water on and below the Earth's surface includes snow, glaciers, ice sheets, sea ice, and permafrost. Approximately 75% of the Earth's total fresh water is stored in glaciers, ice sheets, and permafrost. Snow and ice play a crucial role in Earth's water cycles, such as snowmelt serves as an important source of water in many regions, and interannual variations in snowpack have a substantial impact on regional water availability and can lead to floods and droughts. For example, here is an animation of snowpack in the Sierra Nevada from Terra satellite and MODIS sensor. You can see the snowpack here on the mountain. So snow melt from um, over this region feeds many rivers, and that results in either floods or the droughts if because of the interregional variability. And you can clearly see how the snowpack is changing over time here. Snow and ice also affect albedo, that is a fraction of solar radiation reflected back to space, and that affects energy balance of the entire system, and it can govern temperature of the Earth system by that. So because of that, it's very important to study snow and ice product over the Earth. With that, overall training learning objectives are that by the end of this training, participants will be able to recognize the importance and applications of snow data and snow water equivalent, or SWE, in monitoring water availability in snow-fed rivers, identify NASA snow and ice data products and their applications for water resource management and disaster monitoring, access and visualize snow and ice data products using NASA web tools for water supply prediction, and compares how snow data across platforms are utilized in water resources management and monitoring snow-fed river flow. There is a prerequisite, fundamentals of remote sensing, and link is provided here. It defines many of the concepts that will be used in this training. There will be 3 parts to this training. Today will be on overview of NASA Snow and data products. Next session will be on access and analysis and visualization of NASA Snow and ice data products. And the final session will be monitoring mountain snowpack and prediction of water availability in the western US for water resources and disaster applications. So that there will be a couple of case studies shown here. There will be one homework at the end of this training. It will open on August 7th at the end of the training, and it is due on August 21st. And the homework will be posted on our website. A certificate of completion will be awarded to those who attend all live sessions and complete the homework assignments before the given due date. We'll start with today's session, overview of NASA snow and ice data products. And objectives for today are that by the end of this session, you will recognize the impacts of snow and ice parameters to water resources applications, identify NASA snow and ice data products and their applications for water resource management and disaster monitoring, identify snow and ice data parameters and their characteristics, and explore examples of applications of snow and ice data for water resource management. So outline for today is that we will start with snow and ice geophysical parameters for water resources applications. Then we'll talk about NASA's remote sensing based snow data products, and we'll see an example of snow data application evaluating snow variability through a climatological analysis to support ecological monitoring in Northeast Alaska. Just a note about asking questions. We will have a question and answer session at the end of this part. And so please put your questions in the question box and we will address them at the end of the webinar. Feel free to enter your questions as we go, and we will try to get to all the questions during the question and answer session. The remainder of the questions will be answered in the question and answer document, which will be posted on the training website about a week after the training. So next, I want to introduce our instructors for today, Andrew Barrett and Walter Meier from NSIDC, and we have Ryan Theurer from Airborne Snow Observatory. So Andrew Barrett is a senior associate scientist, and his research focuses on Arctic climate system, in particular on sea ice and terrestrial snow cover. He has an interest in applying machine learning methods to studying these components of the cryosphere. He has also studied mid-latitude glaciers and their role in river basins using model output, satellite imagery, and surface meteorological observations for this research. His specialties are in sea ice, snow cover dynamics, glacier hydrology, scientific software development, and open science. Our next speaker will be Walter Meier, also from NSIDC. He is a senior research scientist at NSIDC, and his primary role is supporting the NASA Snow and Ice Distributed Active Archive Center, or DAC, at NSIDC. In the role, he provides scientific support to all NASA products at the NSIDC DAC, and his research focuses on the sea ice remote sensing, particularly using passive microwave data and tracking Arctic climate change. He is the principal investigator for the NASA-funded Arctic Sea Ice News and Analysis, and is a co-investigator on other NASA, NOAA, and NSF sea ice-related projects at NSIDC. His specialties are in sea ice, passive microwave remote sensing, climate data records of sea ice, Arctic climate change in general, Ryan Theurer graduated from University of North Carolina, Chapel Hill in computer and information sciences, and he has been working with Airborne Snow Observatory as a senior software engineer. His interests are in collecting and analyzing data and finding trends and patterns within data to help guide decision making. So that's what he has been doing with ASO. And today he's going to talk about snow data applications in northern Alaska. It's based on a NASA developed project. So I'm going to hand it to Andrew first. Thank you.
Okay, thank you, Amita, for the introduction. Over the next 10 minutes, I'm going to set the scene for snow and the ice as part of the hydrological cycle and as water resources, and introduce you to some geophysical parameters for water resources applications that we can observe using satellite information and other remote sensing techniques. So what I'm showing here on the screen are two diagrams. On the left is a partitioning of water resources on the globe, and on the right is a cartoon of the water cycle. And if you see in the left-hand diagram, as you would expect for a planet that is 70% ocean, only 2.5% of the Earth's water resources are actually fresh water. And of that, 70% is locked up in glaciers and ice caps. Most of that is in the Antarctic and Greenland ice sheets. And the remaining amount, which is very small, only about 40,000 gigatons, is locked up in mountain glaciers at lower latitudes. We also have snow that, as you can see in the water cycle diagram, falls from precipitation in high latitude and high mountain regions. And that's about 3,000 gigatons at maximum. Generally, for the Northern Hemisphere, that's in March. So there's a large amount of water that we have on Earth is both snow and ice, and is important as a water resource. And I want to demonstrate that in the next two slides. So snow and ice are really natural storage reservoirs. When snow accumulates at high latitudes or high elevations, water can be stored for days to months. Glaciers that form as a result of snow accumulating over many years store water for hundreds to tens of thousands of years being the natural cycle of ice ages. And so meltwater from snow and ice is an important contribution to runoff, especially because of this storage in basins that have less precipitation in spring and summer, which is the growing season. So for agriculture, it's important. What I'm showing here on the right is a diagram from a paper published by Meier in 1969, long time ago, but it sets the scene really well. It shows the precipitation distribution and seasonal runoff for three basins in the Northwest United States: a low elevation, a mountainous snow-covered basin with no glaciers, and a glaciarized basin, so a basin that has both snow and glaciers. And in the top diagram, you can see that the runoff graph shown by the cross-hatching pretty much follows the seasonal distribution of precipitation. In the mountainous basin, the peak runoff is delayed until spring, which is later than the peak of precipitation in winter. In the glaciarized basin, that runoff is delayed even further until the summer. So you can see how much of an impact snow and ice in a basin has on the timing of runoff. And that's important, obviously, to agriculture and other water users. And it saves us having to have reservoirs, man-made reservoirs in those basins. So we've seen how it affects timing, but how much water does in these basins does snow and ice provide? What I'm showing here is a diagram based on some work done at NSIDC, led by Richard Armstrong and funded by USAID, which shows the contribution of snowmelt and ice melt to runoff for 5 basins in high mountain Asia. And you can see here that snow on land and snow on ice make up a significant, if not the largest portion of runoff contributions in all of these basins. In the Ganges, the summer monsoon provides a lot of rainfall, and so snowmelt is not so important, but still kind of getting close to almost 50% of the runoff. You should also note that the glaciers, in this case, don't provide that much runoff, especially in these large basins. It's sometimes important very close to glaciers, but when you get to the continental scale, the contribution of glacier ice to runoff is not as important as snow. If we look elsewhere in the Earth, the Colorado River, for example, in the western United States, 70% of that runoff is provided by snowmelt. So snow and to some extent ice in some cases is really important as a water resource and as a contribution to runoff. So the question as water resource engineers and hydrologists we're asking is, how much snow is there in a basin? And I'm going to focus on snow more than I am ice here. So the question is, what mass of snow do we have in a basin, or what volume of snow do we have in a basin? And often we express that as that volume of snow in a basin as the equivalent volume of water, which we call snow water equivalent. And you can think of that as how much water do we get if we were to melt down the snow, right? So we're not thinking of volume of snow, we're thinking of volume of water we get from that snow. We might also be interested in snow thickness or snow depth, and I'm going to use thickness and depth interchangeably here. And so when we want to answer those kind of questions, at a point, we can do that relatively easy, although it's sometimes physically demanding, by digging a snow pit and measuring the thickness and the density of that snow and coming up with a mass or a volume based on that. And you can see someone doing that here as part of the NASA SnowEx campaign in a snow pit on the Grand Mesa in Colorado. You can see they've used a density cutter to cut into the snowpack and measure density and measuring the thickness of snow there as well. Or, as you see in the bottom photograph, you can take a snow core and you can either weigh that or you can take the snow and melt that down. And these two hydrologists here are using what is called a Mount Rose or federal snow sampler, which is basically a long pole that cuts a core out of the snow and can then be used to measure snow mass or volume. So we can do that at a point, but finding how much snow we have at the basin scale and at the continental scale is a little more difficult. And that's really where remote sensing comes in. And so the parameters that we can get at from using remote sensing are pretty much the same as I introduced: mass, volume, but also area. So we can get at mass directly at a very coarse continental scale by using gravimetry, with using satellites such as GRACE, which measure the Earth's gravitational field. And we have to use a lot of ancillary information and make some assumptions about how groundwater is changing, how runoff is changing, how mass is changing within that basin other than the snow. But we can get at least an estimate of the mass of snow in a basin. We can also measure snow-covered area, as Walt Meier will explain. Snow is very bright, and so we can see that quite well from space, assuming there are no clouds. And we can use that snow-covered area in conjunction with modeling to estimate snowmelt runoff. We can use it as input to models. And we can also derive empirical depletion curves, which relate snow-covered area to the volume of snow in a basin. We can also measure snow thickness and depth and extract volume from that by using LiDAR, either airborne or satellite-based LiDAR, which allows us to measure the distance from the platform, the satellite or airborne platform, to the snow surface. And then if we know where the land surface is beneath that, beneath that, we can get thickness. But in order to get volume, we need to have some information about snow density. So again, we have to make an assumption. We have to use a model. And we can do that. We have models of density, and we can also go out in the field and measure density. And we can also get at snow water equivalent directly, retrieved from passive microwave brightness temperatures. But again, that has some complications. The signal is influenced by many factors: snow crystal size and shape, snowpack temperature, density, and other factors, which means we have to try and model or understand what those influences are in order to extract snow water equivalent. There are other snow properties we can measure that are useful for modeling, such as albedo, grain size, and impurities. And we can get all of those from remote sensing and combine them with modeling and other information to come up with good estimates of snow. So with that, I'll finish and let Walt tell you about the techniques and the platforms and the data sets that we have available to get at some of these parameters.
All right, thanks for the introduction. I'm going to be talking about NASA's remote sensing-based snow data products, particularly those that we have at the National Snow and Ice Data Center, Distributed Active Archive Center, or DAC. It's part of the NASA DACs. So first, I'm going to give a little bit of overview of the type of instruments that we use for snow remote sensing, satellite instruments in particular. We can use passive microwave instruments. This is emission from the Earth that is detected by satellite sensors or other sensors. And the emission that comes from the bare ground that would go to the sensor, that is scattered or attenuated by the snow cover. So it changes, the snow cover changes the emission received by the sensor, and we can detect that change. Visible wavelengths, this one's fairly obvious. Snow is white, so the reflectance or the albedo that is very high for snow can be used to identify snow covered versus bare ground, as well as infrared wavelengths, and I'll talk more about that in a little bit. LiDAR, or laser altimeters, measure the distance from the sensor to the surface, and so when the reflection of the altimeter bounces off the snow surface, it's a higher level than the bare ground, and we can measure that height difference and measure the snow depth. Radar, or synthetic aperture radar, SAR, is an active microwave sensor, and it's similar to the passive microwave. It behaves similarly with snow cover. The snow cover attenuates and changes the backscatter that you get from the sensor to the sensor. And it's active microwave though, so it's a little more, it's powered from the sensor. I'm going to focus here on the passive microwave, in particular the visible and infrared wavelengths, because those are what are most commonly used for snow remote sensing by satellite particularly, and those are the products that we have at the NSIDC DAC. So for passive microwave emission, as I mentioned, you're detecting the energy in the microwave frequency emitted by an object, emitted by the surface of the Earth. And that emitted energy is dependent on the frequency of the microwave that you use, the temperature of the object, and then the properties of the object, particularly the liquid content and water content and the phase of the water content, whether it's frozen or liquid. And brightness temperature is the parameter that is retrieved by passive microwave sensors. It is a temperature in terms of units, Kelvin, but what it really is it's measuring the emission and the emitted energy from the surface. It's basically scaled by to temperature. It's the temperature that would be that it would emit at as a perfect black body, and so it's can be related by a simple equation: brightness temperature as a factor of the emissivity, which is the property of the emitting object in the microwave range, and the physical temperature. And so it's basically scaled by the emissivity again, which is property of the sensors. For surface remote sensing, the microwave frequencies that are most useful, range from about 1 gigahertz to about 90 gigahertz. Those are frequencies where there's not very much atmospheric emission, so the surface can be seen through the clouds, which is a big advantage for microwave over, for example, visible sensors. And the spatial resolution does vary with frequency. Higher frequencies mean higher resolution, but higher frequencies also means more atmospheric sensitivity, more atmospheric emission, which makes it more challenging, and also less penetration through snow, which makes it more challenging as well. So what's been used typically are 18 or 19 gigahertz and 36 or 37 gigahertz have been found to be most useful for snow. The other frequencies can also be helpful, but the basic algorithms were derived for the 18 to 19 gigahertz frequencies and the 36 to 37 gigahertz frequencies. So the instruments that we have data for and that we've used and researchers have used for retrieving snow properties, two sets of sensors primarily. There's the U.S. Department of Defense Meteorological Satellite Program, DMSP, which launched a couple series of sensors, the Special Sensor Microwave Imager, SSMI, which operated from 1987 to 2008. And then a successor to that with some overlap was the Special Sensor Microwave Imager and Sounder, or SSMIS. These are pretty much the same sensors as far as snow remote sensing is concerned, essentially the same resolution, the same frequencies. The sounder adds some atmospheric sounding channels and frequencies that are not used for the snow cover. SSMIS began operating in 2003 and is still operating, but actually is on track to end operations at the end of July, actually, of 2025. And so that will be going away. The other sensor, which is a little more advanced, the Advanced Microwave Scanning Radiometer, there's two of those that have been operating. One is AMSR-E, the Earth Observing System. It's operated from 2002 to 2011. That was a joint NASA and JAXA, which is the Japanese Aerospace Exploration Agency, launched and operated that sensor, AMSR-E. And then that was succeeded by a JAXA sensor. NASA was not involved with the launch or operation of AMSR-2, although NASA has derived products from those as a continuity with AMSR-E. And that is still operating. It was launched in 2012. And then there is AMSR-3, also a JAXA sensor, which was just launched on June 28th, 2025. We have, as far as snow products specifically, our main snow products are from the AMSR-E and AMSR-2 sensors, which have been put together as a unified AMSR product suite, or AMSR-U, and that is what's archived at the NSIDC DAC. Now, in terms of passive microwave snow retrieval, as I mentioned, essentially what we're measuring is emission from the surface. It's emission from the ground, and then it's scattered by the overlying, or attenuated by the overlying snow cover. And the amount of energy that gets through the snow up to the sensor is dependent on the amount of the snow and the characteristics of the snow, as well as the frequency that you're measuring with the microwave frequency that you're measuring with. So basically, higher scattering means you get less emission to the sensor. That means there's more snow. And as I mentioned, it varies by frequency as well. So we can use the difference in how much energy gets to the sensor from different frequencies, and that can give us a sense of the amount of snow cover. And in addition to the depth, it's dependent on other properties of snow, like the grain size and the wetness of the snow, how much moisture, how much liquid water there is in the snow. Dry snow scatters less. You get more of a signal straight from the ground up to the sensor than wet snow. Wet snow attenuates it more. Two parameters that are of interest for geophysical remote sensing that are retrievable by passive microwave sensors is snow depth. That's fairly intuitive, the total thickness of the snow cover on the ground. And then snow water equivalent, and that may be less familiar to people, but that's basically what happens if you take a certain volume of snow and you melt it down into liquid? How much liquid do you get? So it gets into the density of the snow cover and the wetness of the snow cover. And in reality, the SWE, as we call it, SWE, snow water equivalent, is simply the snow depth times the snow density. So it's just a scale between those dependent on the snow density. And so those are two parameters that can be retrieved by path and microwave. And you can convert between those if you know the snow density, the snow depth in the SWE. So there are a lot of limitations with passive microwave snow products. A particular one is the low spatial resolution. The emission from the Earth's surface is quite low energy, so you have to, for a given satellite antenna size, you need to get a fairly large ground area that you are sensing from. So 25 kilometers does not give you a lot of detail, a lot of fine detail, and so that's a definite limit of that. You get lower performance in heavily forested areas because the forested areas also scatter emission and attenuate the emission, so you lose energy in forested areas, and then mountainous regions as well. And some of that is related to the low spatial resolutions. You've got high terrain and high variability in the terrain, and at 25 kilometers you really miss that, so it's really hard to interpret and get good retrievals from passive microwave in mountainous regions. And there has been some advancements, particularly in terms of accounting for the forested areas. You can bring in ancillary data that tells you what type of forest and how forested it is, and do corrections to that. But still, there's uncertainties. There's also lake coverage affects that, and that can be important in places like Canada where there's a lot of lake coverage. And then grain size and density also are uncertainties that we make assumptions about a lot of times for those, but we don't know how well those assumptions are necessarily. And shallow snow tends to get missed. Basically, the shallow snow doesn't attenuate the sensor enough. It's not sensitive enough to tell that there's snow cover there in the passive microwave. And shallow snow can be important in terms of the reflectance and how much energy gets absorbed and the water resources. So the answer snow products that we have at the NSIDC DAC, there are 3 products. There's a daily product. So this is updated every day, and that does leave gaps because the satellite coverage is not complete globally, particularly at lower latitudes. You will not get data every day. So a 5-day composite product fills in and you get complete data, but over a 5-day interval. And then a monthly average as a convenience for like a climatology is also produced. And again, these span from 2002 and will continue up through this year, but they are going to be ending in September of 2025 coming up. So the NASA products will not continue forward, although the AMSR2 sensor is still operating, and then they will continue on with AMSR3 from JAXA, but those will be products that will only be available from JAXA. This is just an example of what you get out of like AMSR2. This is a 5-day average. So again, this fills in all the gaps, which is nice. And you can get the snow water equivalent. This is from March. So this is kind of a late winter field. There's quite a bit of snow cover, particularly at the high latitudes. And then further down in Asia, into the Tibetan Plateau region, some in Europe, and then into the lower southern Canada and the United States, continental United States. So now moving on to visible and near infrared wavelengths. Visible and near infrared, you have to look for atmospheric windows, areas where the energy gets through the atmosphere to the sensor, and so there are certain regions in the visible as well as the near infrared and shortwave infrared there where we can get surface retrievals through the atmosphere, except for through clouds. And moving on, the thing with snow cover in the visible is that it's a very high reflectance, and it's an atmospheric window that transmits through. So this figure I'll explain initially here. The green line with the filled area, in the rainbow of colors in the visible, and then the pink out in the infrared, that is the transmittance through the atmosphere. So the high levels is near 100%. That means that's an atmospheric window where most of the energy gets through. Where it's low, where it's mostly white, that's where the energy tends to be blocked, and you don't get energy from the surface through the atmosphere. And then the solid thick lines are the reflectance of the surfaces there, how much energy in the visible or infrared range from the sun gets reflected back and potentially up to the sensor. And so snow, you can see, is in the visible range. That's an atmospheric window, so that's where we can see the visible light, we can see the sunlight. But snow is very high reflectance there, as you can see. It's near 100%. It's generally around 90% for white, for pure snow, and it's also pretty equal across that entire visible range. And that's why snow is white. It reflects all visible wavelengths pretty much equally, and so that's why you see the white snow. Much more reflective than, for example, the bare ground like rock or vegetation, or liquid water like lakes or rivers. And so you can really see it in the visible range quite well. But the other feature of snow is you get into the infrared range, the near infrared and shortwave infrared, the reflectance drops quite substantially. It gets quite low as you get out towards about 1.5 microns, you can see. And so in the near infrared, it reflects very little. And so there's this big contrast between the visible reflectance of snow and the infrared in the near infrared and shortwave infrared range. And we can use that to detect the snow cover. Before we get into that more, the multispectral sensors that are used for snow retrievals that cover the visible out through the near infrared and shortwave infrared, there's been 3 main families of sensors. The original, going back to 1979, is AVHRR, Advanced Very High Resolution Radiometer on NOAA polar orbiting satellites. It's also continuing on European METOP satellites as well. But that's an older technology, even though it says Advanced Very High Resolution, and that's really been replaced by MODIS, the Moderate Resolution Imaging Spectral Radiometer, which began in 1999, still continuing, and that was on the NASA Earth Observing System satellites Terra and Aqua. And again, those are both providing data, although MODIS is due to sunset in the coming year or so in terms of the data production and sensing, because it's being replaced by VIIRS, the Visible Infrared Imaging and Radiometer Suite. There's now 3 VIIRS flying, one on the MPP, that's the MPOS Participation Project, a preparation project, and then the NOAA 20 and NOAA 21 satellites. And those are all still operating and collecting data. And VIIRS is quite similar to MODIS. I'll show you here the different channels that we have for AVHR, MODIS, and VIIRS. AVHR is only 5 channels, and so it's pretty limited in terms of what you could do, although it's potentially that you can get snow cover from it, but really the main snow products from these multispectral sensors come from MODIS and VIIRS. MODIS has 36 channels, spanning from the red in the visible all the way out to thermal IR. VIIRS essentially covers those same channels with slightly different frequencies and wavelengths that collect data. In terms of the resolution, MODIS and VIIRS are cross-track scanners. This is a bit different than the microwave I didn't mention earlier, but the microwave are conical scanning basically in a circle. So the resolution is consistent across the entire scan for microwave. But for multispectral sensors, they're typically cross-track sensors, which means they scan back and forth kind of horizontally as the sensor is moving. And that means that the angle that you're sensing from changes. And that also means that you're collecting data from a larger area, which means the sensor's instantaneous field of view or footprint change, and that means your resolution changes. So you get the highest resolution at nadir directly below the sensor, and as you go out and scan out to the side from the sensor, that resolution gets lower. And so you end up, when you collect these data, when these data are collected, you actually start overlapping footprints as you get further out along the scan line, and you get what's called a bow tie effect, and kind of get overlap and between the footprints and kind of they're kind of stepping on each other in a sense. And so you get, if you look at just the raw data, you get this kind of overlapping, and you get these black bars in the raw data. But the onboard sensor processing takes care of that. They're removed, and so you get kind of a nice field of view. But the resolution is lower as you get out away from nadir. So nadir's on the left here, right under the sensor, and this is showing just one side of the scan as you get out farther. All right, so going back to this figure here showing the reflectance and the atmospheric transmission. Couple of the wavelengths that are on VIIRS, and MODIS again has similar wavelengths. The 0.64 kind of in the red area, you have the snow has very high reflectance there, and then going out to 1.6 microns, which is out towards the shortwave infrared, you can see there it's very low. So you've got high reflectance in the visible, very low reflectance in the infrared, and so that contrast gives us a really nice way to pick out the snow cover very easily. And so what's been developed a long time ago actually is the normalized difference snow index, or NDSI. So this is the NDSI equation for VIIRS. Again, there's a similar equation for MODIS, just slightly different wavelengths that are used. And it's just the difference between the visible and the shortwave infrared, just the difference in the reflectance, and then normalized by the sum of those two. So you kind of eliminate other factors and you get a unitless number there. And essentially, visible for snow is high reflectance, shortwave is low. For vegetation and bare ground, the opposite tends to be true. The shortwave infrared is more reflective than the visible. And so if it's less than zero, if the NDSI is less than zero, we know it's not snow. If it's greater than zero, then it definitely could be snow. But low values that are greater than zero may not be snow. But if we get to higher values, like greater than 0.4, then it becomes very likely snow. And so we can use that as a threshold, and that's commonly used as a threshold. So, bottom line, if NDSI is greater than zero, snow always has an NDSI greater than zero. But if it's greater than zero, we don't know for sure it's snow unless it gets to a certain point, a certain magnitude. So I just go through a quick example here. This was a snowstorm in the Colorado region near Denver. This is near where National Snow and Ice Data Center is. And March 25th of 2013. This is a true color image from NASA Worldview. So this takes 3 channels and from the red, green, and blue, composites them together to get something that looks like we normally see with a camera or with our eyes. And you can see here the white snow cover covering much of the plains of Colorado and then into the mountains. Denver there is annotated. You can see it's not quite as white in Denver due to all the infrastructure and buildings and streets and so forth, and so it gets you lose some of the snow cover there in the whiteness. So if we look at the reflectance band, this is from MODIS. So this is at 0.55 microns, but similar to the Beer's 0.6 that I talked about. And this is a scaled reflectance, so it's just basically saying high reflectance versus low reflectance, not scaled to 0 to 1, but giving you the relative reflectance. And you can see the very bright red, that's very high reflectance east of Denver to the right, and then also in areas of the mountains. But you see Denver, there's kind of a bit of a hole there due to the fact that the city and the streets and so forth, the infrastructure there. So very high in the visible range and in the red range. And then here, very low in the shortwave infrared. This is the 1.6 microns. And again, you can see quite low values, much lower in the blue low end of the scale there. So you put those together into the NDSI, and you get, this is again scaled 0 to 100. The NDSI generally goes between 0 and 1, but the scaling here is given as 0 to 100, so it's just a difference in scaling. But again, you get quite high values east of Denver in the orange and reddish colors there. Again, Denver doesn't really get retrievals there because of the city, and then there's also other blank spots due to clouds, and where it's not getting data from that. But again, this shows that you get these high NDSI values from the snow cover. And then this is this is from Worldview, the same, just showing a different. This is now scaled 0 to 1, and again, pretty vast areas of high NDSI values that are snow covered, except again for the area of Denver due to the infrastructure. So limits of these snow retrievals from the visible and infrared sensors. A big one is clouds. You don't get data from under clouds. The clouds reflect to the shortwave and visible shortwave and infrared radiation, and so you don't see the surface. Another thing with clouds is not only that you don't get data, but clouds are white, snow is white, and so it can be hard to distinguish clouds from snow, even with the visible eye. And so there needs to be a lot of effort to kind of clear out the clouds and make sure you're not getting clouds in these products instead of the snow. So there's a lot of tests that are done. It combines several different channels to create cloud masks and mask the clouds, particularly and specifically for the snow cover. And then there are cloud gap products that fill in using composites and other methods to kind of fill in where there are clouds so you can get complete coverage. But fundamentally, where there's clouds at a given time, you cannot get data. Nighttime, infrared, you might get some retrievals from that. But generally for visible in any kind of shortwave without the sun shining, you're not going to see, you're not going to get any retrievals. So these are, the snow products are pretty much daytime only. Vegetation can alter the reflectance, so that's another thing. Heavily forested areas, if you are familiar, sometimes those get snow covered, but maybe not. And then the vegetation will make it look darker than it is in the visible range, for example. And then cities, populated areas, lower reflectance, as I showed for Denver. There's also the issue, especially in mountains, shadows and oblique incident angles. You don't get the reflectance retrieved because of those, because you're not getting that reflection in these shadow areas, and so you won't get data from those. So another example, more recently, this is March 15th of 2025. This is a full North America example. This is the True Color composite, and this is the NDSI from Beer's. You can see it gets, there's a lot of snow cover, but there are patches there that, look like they probably should be snow covered, but it's not being retrieved. And that's due likely to clouds or the cloud masking. And the cloud masking is pretty conservative because you don't want to get clouds where you think there might be snow. So it tends to err towards detecting more clouds than not. So it may, some areas that may actually be clear may get masked as clouds just because of the way that these tests are done to make sure, or try to make sure, that you don't get false snow due to cloud cover. And the one thing with the AMSR in the microwave, it's not affected by cloud cover. So we can actually combine these potentially. And so that fills in, you can see here where if I toggle between these, these areas that are, there's no snow retrieval from veers, but they actually are snow covered over much of that. It's just cloud, or at least masked as cloud. And AMSR gives you the data there in that area, but at lower resolution, you can see it's more pixelated, and it's giving you the snow water equivalent, but it does fill in areas there where there is snow cover. So there are several different MODIS snow products covering different aspects and different resolutions. The basic one is the swath, getting with each as the MODIS sensors orbit each time around the Earth. It's a level 2 product. 500-meter resolution. It gives you the NDSI parameter. The orbits are broken up into what are 5-minute orbit parcels. And so to make the data volume reasonable to download, and allows one to get data over only or area of interest instead of a whole orbit. And then there are gridded products. They have these sinusoidal gridded tiles at 500 meters, and then they are binned up. One thing with the MODIS in the veers is that, for each grid cell, each footprint, it's giving you the NDSI is a threshold. It's giving you either snow covered or not snow covered. It doesn't give you a fractional snow cover, but if you bin these up into bigger grids, like a 0.05 grid, like the mod 10C1, that gives you the percent snow cover. And so again, these there are several different products. There's also a climate model grid products that are useful for climate models. The grid is comparable to what's used in climate models, so it's easier for modelers to ingest those data into their models for assimilation or validation. And then there are also these 8-day composite products, and that helps fill in where there's clouds and give you more complete areas instead of the gap, the daily products that have gaps. And then there's the mean 1-month mean product. And I listed here these MOD products. These refer specifically to the MODIS products on the Terra satellite. I mentioned earlier it's also on the Aqua satellite. There are, to save space, I didn't list those, but those are exactly the same products, but they are denoted by MYD instead of MOD. And so they're the exact same products, just from the Aqua sensor. Currently, we're on version 61, or collection 6.1 as it's called, at the DAC, all in HDF EOS 2 format. The version 7, collection 7, will be coming out in the future before too long. Then the Veer snow products are similar. There's not as many products at the current time. And we have these VMP products. That's the MPP satellite. There's also, I mentioned the NOAA 20, that is denoted by VJ1. There's also NOAA 21, which we do not yet have in the DAC, but those will be coming before too long. Version 2 is currently available at the DAC, and these are in HDF EOS 5 format. And again, there's the swath data. These are broken up into 6-minute intervals, different than the MODIS 5-minute. The resolution's a little bit different, but then it also has these sinusoidal gridded tiles, the climate model grid, and then a gap-filled product also for daily that uses ancillary data and filling methods to give you a cloud gap-filled product. So There's been improvements over the years to these products, but one of the big improvements is to look at the signal that you're getting and understanding that it's not just snow or not snow, it's a mixture of everything that is within that footprint, vegetation, soil, rock, whatever. And all of those things contribute to the surface type. And you can actually use these, multiple frequencies, different bands, to do what's called spectral unmixing, which basically, instead of just giving you a threshold like the NDSI, it actually tries to put together how much reflectance is coming from these different components, and it can solve for not only snow cover or not snow cover, but also the properties of grain size, and then radiative forcing due to dust. So snow is generally white, but you can get dust on the snow, which changes the albedo. This comes straight from the surface reflectance product. And this is developed originally by Thomas Painter, and then it's been carried forward by Carl Richter at the University of Colorado here. And he will talk about this product more in part 3. So I'm just giving you a quick overview of this, and I won't go into much detail, but just to show a couple examples, it can give you on the image here on the bottom left, the snow-covered area, and then on the bottom right, the grain size, and then as well as RGB composites, and then it uses the elevation as well to help with the reflectance. And so in ancillary data, and again, there's been advancements of this. There's a newer spatially and temporally complete STC product, and these products are being produced at NSIDC. I'll talk about that in a minute. There's also another advancement called SPIRES, Snow Property Inversion from Remote Sensing. This is kind of a carry-on from the SCAG and DRFS. It has optimized processing for a larger number of pixels, and then it solves these light-absorbing particles, or dust, essentially is what that's referring to, in grain size simultaneously. And this is nice because it's adaptable to any sensor with channels from visible to the shortwave IR. And again, I mentioned these are now being produced and provided by the NSIDC DAC, currently for MODIS, but it's being adapted for VIIRS as well. And I put this here mostly just for reference, and like I said, Carl will talk about this more, but this just kind of shows the comparison between those and how they're put together. The main thing is this light attenuating particle, the way it handles those. Instead of doing it separately for the SCAG DRFS, it does it simultaneously for SPIRES. SPIRES is still under development, whereas the SCAG DRFS is pretty much complete in terms of its development and being transitioned to the DAC. One of the places this is getting used is in the Snow Today website. This is an NSIDC website that provides, during the Northern Hemisphere snow season, focused currently on the Western US, providing the snow cover statistics and images based on the MOD, SCAG, DRFS, and the SPIRES. Funded through the NASA Terrestrial Hydrology Program, and Carl Richter at INSTAR in the University of Colorado leads this. And so this is updated through the winter season. Images are updated every day, and then there's also analyses published about once a month on how this is put together. And this again will be talked about more by Carl in part 3. All right, another mission that NSIDC DAC has data for is called the Airborne Snow Observatory. I've talked mostly about satellite observations, and those are useful because they're continuously flying. We have a long history of data, but there's, as I mentioned, a lot of limitations in detecting snow cover from these satellite sensors. There tend to be individual sensors that can't resolve all of the relevant properties. The spatial resolution is still coarse for a lot of important local and basin scale details that are needed for water resources. So back in 2013, NASA Jet Propulsion Laboratory put together the Airborne Snow Observatory ASO mission. And that was again developed to quantify snow water equivalent and snow albedo for mountain watersheds at a high spatial resolution. So trying to really get very detailed information and really improve the knowledge of snow properties and how they vary in different types of airborne sensors, and get the spatial and temporal variability. And the idea is that these will be really useful input data for future water management models and water management systems. This was a collaboration with the California Department of Water Resources and focused really on the Sierra Nevada area. And the NASA support for this NASA mission lasted until 2019. And then ASO became a commercial entity, ASO Incorporated. And so it now exists as a commercial entity. And again, it focuses primarily on the Sierra Nevada mountains and California water resources. And their data is currently available through the ASO Incorporated. It is not publicly available for free, but the NSIDC DAC does archive the historical ASO data from the NASA mission, and that is available freely, as all other NASA data is. So the instruments that ASO use, one is a scanning LiDAR laser altimeter to get snow depth, and that has not been used much and not from satellites much, especially when ASO started out. So that's a unique instrument, unique data product. And then the imaging spectral radiometer to give you albedo, and it has enough channels that can look at changes in snow grain size, dust, black carbon, other organic model. And then it combines these with a snow density model as well to really put together a detailed set of parameters that are very useful for water resources. This is just an example, the Tuolumne River Basin back in 2014 in California. And you can see, a lot of detail here, and all different parameters: the snow depth, the snow density, the snow water equivalent, and the albedo. And these are all really important impacts for understanding the hydrology, understanding water resources, how the drainage and how the water supply will work out in the summertime as the snow melts and you have the runoff and the snow runoff. And so this is really valuable data, but as a airborne mission, it's pretty limited in how much data you can collect. So it's focused on very specific watersheds that are key for customers of ASO. So these are the products that we have from ASO. There's they're pretty much all the LiDAR retrievals. And again, these are 2013 to 2019. One final product that we have that I want to note is from the SnowEx mission. And these are a series of NASA, both airborne and field campaigns that took place between 2017 and 2023 in the Western United States, mostly in Colorado, but there was one in Alaska as well. This was funded by the NASA Terrestrial Hydrology Program. And SnowEx, like ASO, involves airborne, but also brought in ground measurements, field measurements. And the goal was to really more accurately measure snow characteristics in a variety of terrain and vegetation canopy, in terrain and vegetation canopies that are really well understood and we have good data from. And so there's ground measurements taken in the field and then validated against airborne measurements. And it allows one to compare different remote sensing technologies. And the hope is that these data can inform future potential snow satellite mission design. There has not really been a snow satellite or a snow satellite mission by NASA or really any space agency focused specifically on snow and having the instruments that are optimized for snow. So SnowEx really worked towards trying to understand the instruments and the data from the different instruments and what would be an optimal combination for those for such a satellite mission. I'm not going to list all of the data sets because there's just so many. There's about 100 data sets spanning all different kinds of data. There was airborne LiDAR, there was UAV, SAR, there was snow water equivalent data collected in the field and snow depth collected, ground penetrating radar from the ground, surface spectral reflectance, snow pit measurements. There are some folks digging a snow pit, and then the meteorological data to understand the conditions and how those were changing and how that affected the snow cover. This is just a quick example. This is an example of comparing ground penetrating radar, which is on a sled, pulled on a sled that's down in D there in the lower right. The data, the returns in A, and then the red is what was derived as the snow depth there in the top in A. And then it's compared in blue, the DPR, with snow stakes and snow probes that were stuck in along the same transit there. Those are the red lines. And you can see the red lines extend a little bit deeper than the GPR. So there's good comparison between GPR as far as the variability along the track, but there's a bias compared to the snow probes. And then the left there just gives you a sense of where that was. It was in western Colorado, in the Grand Mesa area there. So this is really dense data, really useful, something you can't get from satellite or even airborne. This really fine-tuned, high-density validation. So with that, I will finish up. Here's resources on the different sensors, and these include links to the data as well as some informational resources there, like the NASA's Got Snow page, and then Snow Today, and then references there to the relationship between glaciers and snow and water supply. So thank you very much.
Yeah, thanks for the introduction. Hi, everyone. My name is Ryan Theurer. I'm a senior software programmer for a company called Airborne Snow Observatories. But I volunteer on the side also with the Develop program as a science and technical advisor as well. Just to give a little background on Develop, participants are selected for the program, and they conduct like 10-week studies in interdisciplinary teams of like 4 to 5 people. And they work closely with Develop science advisors and mentors and NASA partners on real-world projects and problems. And through this process, they learn how to use Earth observation science for various things from climate research to disaster detection and other things of that sort. So in 2023, I had the pleasure of advising the Northeast Alaska climate team, whose members were Christian Anderson, Omid Aruji, Isabel Chitamuri, and Thomas Gurman. The main objective of this project, which I'll be presenting, was to evaluate snow variability through a climatological analysis to support ecological monitoring in Northeast Alaska. So going on. So our study area is comprised of the National Petroleum Reserve of Alaska, the NPRA, as you can see on the left, and the Arctic National Wildlife Refuge, which you can see over on the right. The range which we're going to be looking at is between the years 2000 and 2022. These lands are administered by the Bureau of Land Management and the U.S. Fish and Wildlife Reserve. And just to give you a quick view of the topography of these areas, as you can see, the NPRA has a lot of flatland Arctic tundra to the north and some mountainous regions down to the south, going up into the slopes. And then the ANWR, a lot of mountainous regions, some kind of coastal tundra up in the north as well, and some mountainous regions throughout the center of it, going through the Brooks Range. So the community concerns that were addressed in this project cover a whole lot of different areas, including mainly snow cover loss and how that affects everything from transportation in these areas to oil exploration and how they use seismology to detect different new reservoir sites and how these can be accessed and how those can affect the ecology of the area. How Variability in snow cover has affected biodiversity in the area, and also has affected the indigenous people who live in that region as well. So the partners for this project were the U.S. Fish and Wildlife Service and Arctic National Wildlife Reserve and the Alaska Climate Adaptation Science Center. As I mentioned in the last slide, the main focuses of what these partners were looking for were just to see how not only the ecology has been affected as climate has shifted over the last 2 decades, but also how it's affected everything from transportation up in that region to the ecology to how wildlife exists in that region as well. So the first objective was to evaluate historic snow variables, including snow cover, snow water equivalent or SWE, and snow depth, to understand how changing climate has affected each one of these variables. One of the 2 main snow variables that we looked at were both snow depth and snow cover fraction. We're trying to create end products such as like time series analysis, snow variable maps, and snow on and off maps to look at the trends across these 22 years and see if we could provide our partners with a end product that could help them figure out how this area or how these 2 areas were changing over that amount of time and how they could continue to change in the future. So MODIS is a sensor set aboard the Terra satellite. The data set uses gridded snow cover and albedo derived from radiance data. Snow cover is, the snow cover data set is identified using NDSI or normalized difference snow index, which is a data set that goes through a series of screens to alleviate errors and flag uncertainties such as radiance angle and whatnot to throw out unreliable data, and then is able to use different band indexes to figure out whether snow is over a certain pixel or not, or contains a certain percentage of snow. The NASA model based on the Global Land Data Simulation System, or GLDAS, is a snow depth product, was also used. Was a new data product at that time that determines snow depth with a combination of observation and model data from NOAA and also the Air Force Weather Agency's agriculture meteorological modeling system. So this data was acquired and then using Google Earth Engine and the Python API associated with that. Pretty much the team got the data sets for these, downloaded them directly through their browser using a Google Earth Engine, and then was able to filter on those regions, get those products, and then visualize and experiment and create charts to explore the data set and see over these 20 years whether there were any meteorological trends that could shed light on what our partners were looking to get out of this data. So for the NDSI snow cover, we first reclassified the snow cover values as binary classification. So any value from 0 to 14, 0 to 14% being 0 being no snow cover at all, up to maybe a 15% cover of that pixel, we determined as a non-snow pixel. And then from 15 to 100, we set as 1 to indicate as a snow cover pixel. We use those masks to kind of sort the data out into this kind of simple binary snow cover map, which then we use to look at how snow covered these areas. And a lot of this data and quality assessment can be found within the NDSI snow coverage algorithm flags within the data set itself. So each pixel, we then mapped all these data on top of each other and determined over each season or each year, every time the pixel changed from 0 to 1 and 1 to 0, pretty much showing us the variability of that area's change in snow coverage. The team was also able to, using this data set, figure out the first and last day of continuous snow for each snow season, so they could better map out how long these snow seasons lasted in these two specific areas in Alaska and how they've changed over the years as well. So one of the first things the team looked at were the monthly snow cover rates between all these years. As we can see here in both regions, we see what we would expect, where snow remains really high in the winter months, starts to melt in May, and then in the summer completely drops out and melts, and then builds back up during the fall and winter season. We saw this consistently throughout both regions. But one thing that was interesting to note was in the NPRA in the winter months like December and January, we had to cut data from these months because data wasn't available due to polar nights. So during the winter time up in these northern regions, the sun sets completely and there's no daylight, so there's not an ability to get data during these times. So we had to throw out data from those months for this region in particular. Furthermore, kind of looking at monthly snow covered fractions, the team broke all the years into 4 seasons, and then were able to plot them across the 20 years span. And as we can see, similar kind of results as far as where we expected snow cover to be during which seasons. These maps show the change in the last day of snow per year. The darker blue is later in the year, and the warmer colors are earlier in the year. For example, this area that we can see in the first arrow has snow lasting till October, while this area where the second arrow is showing up has snow until July. Over time, we can see the areas that have snow the longest lose snow first, and more importantly, areas that change most often from year to year and where that variability is showing up most. So as we can see, the mountainous regions certainly have the most variability, jumping from high to low pretty quickly. And you know. So the team was also able to look at season start and end dates and how those have changed over the last 20 years. The map on the left shows the difference between the first day of snow in the year 2000 and the last day of snow in the year 2022. The blue color indicates that this date is coming later in the year, while the red color indicates the date is coming earlier. These maps indicate that across the majority of both regions, except for the southern portion of the ANWR, the snow seasons are beginning later into the year. Although it should be noted, throughout this project, the variability from year to year to year was in between years was pretty variable. And we'll see later, while trends were pointing towards later snow season starts and earlier ends, the variability was so high that it was hard to really nail down a very definite trend in that. And yeah, as we can see here, this is what they plotted out for all 20 years together. And while, yeah, we see a negative slope here, variability is so high that it's hard to really get out a really clean trend out of this. Yeah, moving on to snow cover variability. This slide shows 2 GIFs. One is of the NPRA, the petroleum region, and the other one is for the ANWR. These GIFs over time show how snow cover starting in January and going through December. The image is color-coded to indicate areas with high variation in yellow and areas with low variation in blue. So as you can see on the left, that the northern coastlines have the highest variability in June, as snow is melting out over in these coastal regions. We can also see the pixels switching on and off between snow throughout the years more frequently as it gets farther out. We can also see in the mountainous regions of the ANWR on the right how snow is kind of sticking around in the mountains as well. Okay, and then going to our other snow product, the snow depth. Snow depth was similarly binned like our snow cover, and average snow depths were taken for each pixel. For the NPRA on the right, or on the left, excuse me, you can see that snow depth is quite uniform across the whole region, but for the ANWR, the wilderness region to the right, it appears that the mountain ranges have the highest amount of snow cover over the longest period of time. However, as you can also see from this data, the resolution size is poor because it's 27 kilometer resolution. No solid conclusions could really be made by the team about how snow depth was being held in what specific regions over these 20 years. So in conclusion, the team found that in the ANWR, the snow cover variability was greater in the mountainous regions, whereas in the NPRA, snow cover variability was greater in the coastal regions. No significant trends were found in snow season duration in both regions, likely due to frequent changes in snow season start and end from various blizzards and events across these 20 years. But for both NPRA and ANWR, we saw the average snow depth steadily increase as you approach the Brooks Range, which, as we would assume, the highest amount of snow depth kind of staying in the mountains over these time periods. So the team's analysis was limited to spatial and temporal resolution of the MODIS and GLDAS data products. The data resolution of 500 meters and 27 kilometers respectively for both products limited their ability to capture snow variability at these smaller spatial scales. The accuracy of their data may have been affected in the data by like polar nights as well, kind of obfuscating their data in the main winter months for the petroleum region. And then other things such as like cloud cover and other environmental factors might have also affected data quality as well. Yeah, just ending up, we wanted to give some last shout outs to the others that helped with this project, including Catherine Caruso, which was the NCEI fellow that helped the team, Dr. Kent Ross, who's the science advisor at Develop, Julian Dan over at the University of Alaska Fairbanks, Dr. Bob Bolton, who's at the International Arctic Research Center, Dr. Jesse Cherry, Molly Wallazin at the National Integrated Drought Information System Center, and our other partners, Dr. Jessica Garin, Dr. Paul Leonard, and other support from other NCEI fellows, Brooke Adams, Ellen Bartow Gillis, and Steve Ansari. Thank you.
Thanks, Ryan. And thanks to all our guest instructors, Andrew Barrett, Walter Meier, and Ryan Theurer, for their excellent presentations about snow data and their applications. And so this brings us to the end of today's webinar. So we want to summarize what we saw. Snow and ice are an important water resource, as we saw. Snow and ice play a crucial role in Earth's water cycles. Snowmelt serves as an important source of water in many regions. Interannual variations in snowpack have a substantial impact on the regional water availability and can lead to floods or droughts. When snow accumulates at higher latitudes or in higher elevations, water is stored for days or months. Glaciers, if the result of snow accumulating over years, and it stores water for hundreds to tens of thousands of years. Measurements of snow that includes snow-covered area, snow thickness, and snow water equivalent, as we saw earlier in the webinar. Some snow properties which are also important are snow albedo, snow grain size, and snow impurities. We also saw several products, and here are a couple of tables that will summarize these products. So remote sensing of snow and ice, these missions and sensors are shown here. We saw that spectral measurements, both passive microwave and visible and near infrared spectral measurements are used. Missions for passive microwaves are DMSP, SSMI, SSMIS, and NASA JAXA EMSR-E and EMSR-2. And for visible and near infrared, NOAA 8 to 19, these are operational satellites, and also NASA Earth observing satellites such as Terra and Aqua. They have MODIS on them. NOAA has AVHRR, these are sensors, and recent sensors SNPB and NOAA 20, they have WIRS. These are all visible and near infrared instruments. And temporal coverage is also summarized here. So it's a long-term data sets available from early 70s, late 70s, all the way to present. Just to summarize the products themselves, these are the products available from NSIDC, daily, 5-day, and monthly from passive microwave. And if you go to visible and near infrared, there are MODIS products, which are either swath products, gridded products, and different resolutions, as you can see here in temporal and spatial scales are given here. Monthly mean snow cover also is available to look at variability over seasons. This is from WIRS instrument, and these are the names of the products. We covered this during the webinar, both Andy and Walt did, but this is just a summary for you as a reference. So here also you can see that special and temporal samplings are given for different products. So these two tables will serve as reference for you if you are looking for any particular snow and ice data product. Finally, here are some additional snow products, and we also saw some applications. We saw that there's improvement to standard MODIS snow products based on MODSCAG and DRFS algorithms. So that is MODIS snow cover and grain size and dust radiative forcing in snow. Similarly, snow property inversion from remote sensing or spires, that's also an improvement to standard snow product. And snow today is an application of MODSCAG and spires, and that provides daily updated snow conditions in the Western US and monthly analysis during the snow season. We are going to see details of this in our last session. We also talked about Airborne Snow Observatory, which focuses on primarily on Sierra Nevada mountains and California water resources for snow observations, and SnowEx, which is a series of NASA airborne and field campaigns in Western US, mostly in Colorado and also in Alaska. And finally, we saw application of MODIS snow cover and GLDAS snow depth in monitoring variability of snow in Alaska for National Petroleum Reserve of Alaska and Arctic National Wildlife Refuge. As I mentioned earlier, there will be one homework at the end of this training. Will be open on 7th August, and it will be available from the training webpage. You will submit the homework via Google Forms, and it will be due on 21st of August. As I mentioned earlier, a certificate of completion will be awarded to those who attend all live sessions and complete the homework by the due date. The certificate will be received via email approximately 2 months after completion of the course. With that, we're going to end today's session, and our next session will be on access analysis and visualization of NASA snow and ice data products, the products that we reviewed today. So we want to thank our instructors, Andrew Barrett and Walter Meier, and also contributors from NSIDC, Michaela Beek, Saber Brescher and Diane Fritz. Here is the contact information for our guest instructors, and you can always contact ARSET. This is our website. You can follow us on our YouTube channel, and this is our sister program Develop that you may want to check out. So I want to thank you for attending to this session, and we will move to question and answer session now. Thank you. To everyone. Thanks for attending today's session. We'll move to the question and answer part now. Once again, we want to thank all our speakers, Ryan Theurer, who was presented Develop case study, and also Andy and Walt from NSIDC. The excellent presentation. Thank you so much. We also want to thank our ARSET team before we go to question and answer session. We have several questions. If we cannot go through all of them, we'll post them on our website. So we also want to thank Selvin Hudson-Odoi, our coordinator, Brock Blevins, Jonathan O'Brien, and Sean McCartney, my colleague, who helped me putting this together. So thank you all, ARSET team, for your help with this. Also, want to go through questions, as many as we can. So let's start with question 1. And I request all the speakers to unmute and answer the questions. So what is basin here? So if you want to take that question.
Yeah, hi, this is Andy Barrett. I think the slide you're referring to is the hydrographs and looking at the 3 different basins. Those are all in western Washington state in the United States. So it's on the west coast of the United States. And they're all relatively small basins. I've listed them here, but also listed the paper, so you can go and take a look at that yourselves. The low elevation basin is Day Creek, the mountain basin is South Fork of Nooksack River, and the glaciarized basin is Thunder Creek. But yeah, it's western Washington state.
Thank you, Andy. Second question is, can you please provide the source from where this percentage number is coming about contribution of snow and ice? And please refer to this USGS webpage. There is a figure and there are numbers given in here about freshwater availability, and that's where this is mentioned. Question 3, for LiDAR, how do we measure snow depth over a glacier? Is there any penetration of LiDAR in snow or ice?
Sorry, I was trying to find my unmute button. This is Diane, and LiDAR is going to give you the surface of the snow, so a combination of that surface value with passive microwave or radar data to get the ice surface is going to give you that snow depth in that situation. So if you have a digital elevation model of the ground with no ice, you'll be able to get that snow depth directly from LiDAR. But with that ice in there, using a combination of both radar and LiDAR will get that snow depth.
Thank you, Diane. Next question is, what is the unit of snow water equivalent measurement? Meter equivalent of water or kilogram per square meter?
Both are used, and it depends on the field that you're working in. So I think in water resources and hydrology, we generally think of SWE being measured in meters of water equivalent, but you'll often find within model output, especially reanalysis and climate models, snow may be given in kilograms per meter squared. because the density of water is 1,000 kilograms per meter cubed. 1 meter of SWE is equivalent to 1,000 kilograms per meter cubed, or per meter squared. I should change that in the document. Yeah, so both are used, and it depends on the research domain that you're working in.
Question 5 is, what is the maximum depth of snow that can be measured using passive microwave remote sensing? So we will be answering this question later on with specific details. So we're going to go to the next question. Question 6 is, are there any planned updates or upcoming missions that aim to overcome current limitations in snow retrievals using visible infrared sensors, particularly regarding cloud cover and forest canopy changes?
Yeah, so this is Andy again, and others may have different information or no missions, but as far as I know, there are no specific missions, snow missions planned. There have been a number of field campaigns, CLPX, back in the early 2000s, and more recently the SnowEx campaigns have done a lot of field work looking at kind of to study and evaluate snow retrievals from remote sensing and airborne campaigns, and try and tie that in with actual characteristics of snow on the ground. So we're learning a lot about how these sensors are seeing snow on the ground and how we can improve algorithms and things like that. With respect to clouds and forest canopy, I think there is information from other missions that could be included to help us with getting at this problem. But generally, the approach is to address that algorithmically. So just improving algorithms to detect clouds in better ways. It's still a hard problem. Clouds are bright, snow is bright. With forest canopy, the spectral unmixing approach that Walt talked about with some of the visible imagery can help with forest canopy and seeing snow on the ground. And in fact, that was one of the reasons it was developed. You know, it's part of this mixed pixel problem that we have with remote sensing, in that a sensor can only see a certain area of the ground, and that area can have snow, it can have rock, it can have vegetation, and teasing out and separating out those different components is a challenge. And spectral unmixing and kind of taking that and using machine learning approaches can help, but we generally do it algorithmically.
Great, thank you. Question 7 is, do you have any research on the measuring the greenhouse emissions such as methane gas leakage due to melting down of snow in the permafrost? There are some research papers you can find online, but NASA has this experiment, Arctic Boreal Vulnerability Experiment, or ABOVE, that has some information. This is focused on Alaska, and you will find some methane observations over like frozen lakes, or where when not, so yeah, so in that region. So you can look it up, and we'll also provide some more references for that. Question 8 is, could you recommend some of the decent NDSI applied research or unique research on them?
This is Andy again. I've put there are a couple of references here from the early work done on MODIS. Rosenthal and Dozier evaluated NDSI using Landsat, and but then there's a lot of information in the algorithm theoretical basis document, ATBD, for the MOD 10A1 and MYD 10A1 products. So that you can use that information. There are a lot of applied studies that I think you can find. I just don't have them to hand. And Ryan gave a really great kind of use case of using using NDSI for in Alaska. So yeah, and maybe Ryan can add some studies if he has any to mind.
Oh, yeah, I have to jump on the SnowEx Q&A if there's a link there for it, and I can post some stuff. But yeah, a lot of the, I mean, Jeff Dozier is part of our company over at ASO and has done like a lot of really great work doing like applied LiDAR and particularly with some drone stuff recently for that. And I know Tom Painter, our CEO, has done like a lot of stuff in the past as well. So I can post a few of those as well once I get the link for that.
Thank you. Thanks so much. So I think, yeah, you'll provide that information. Question 10 is, how is the validation results of snow depth in Ryan's presentation? What are the typical error margins or uncertainty ranges in SWE or snow albedo?
So I think a lot of that came from GLDAS, which is like a combination of different models, and then through that combination, kind of estimating the amount of snow depth over a large area. The spatial resolution of that is like really large. I'm forgetting the number off the top of my head right now, but I can't really speak to, because I don't think we dug into it very much after seeing the preliminary results for a lot of the data, especially from month to month, because it was so coarse, the resolution, that it didn't really help with what we were looking at and what the customers were looking for changes in snow coverage over time. So I'm not 100% sure how the range and uncertainties of that data is, because after kind of seeing the results immediately, we just created the plots for it and didn't dig into it as much further. But I don't know if anyone else on the call maybe has a better idea and has used GLDAS before and can speak on that.
Yeah, we will look into GLDAS uncertainty matrix and see if we can provide that information. We'll take one more question, considering that we already are gone past the time. So is there any way to downscale the resolution of MODIS snow cover data? And
So this is Diane again. I took a quick look, but I'm seeing that Carl's putting in some more references. If you look, there are papers published on using random forest regression, other methods, and Carl has an example, but like kind of downscaling this to Sentinel-2 resolutions, for example. So I would look into the literature and find methods and papers out there, and maybe Carl can speak to this more later.
great. Yeah, Carl, if you want to add anything, please go ahead.
Yeah, I think so. I think Andy put that first one in there. So I think you can do machine learning, to combine basically the temporal characteristics of, say, MODIS or VIIRS with the, spatial resolution of Landsat or Sentinel. And I think it's not being widely done, but there are algorithms available to sort of combine those data sets, just to want to make sure you have really good inputs into those machine learning methods before you start combining them so you can get the best available output. So yeah, those papers are good places to start to understand, the current methods. Yeah, that's it.
Great. Thank you, Carl. I think we have a few more questions that we will address and then post the answers online, or this Q&A document will be available from the training website, so you can refer to it later. We're going to end today's session. We hope to see you next Thursday at the same time on 31st of July. So again, once again, thank you all, our speakers, Andrew Barrett, Walter, Ryan, also Diane, thanks for answering the questions, and Carl as well. Also want to thank our ARSET team one more time for their help. Our coordinators, Selvin Hudson-Oddo and Brock Blevins, Sean McCartney, Sue Monty, Jonathan O'Brien, Sarah Carshell, and Maria Marabito. They all have contributed to this training. So thanks, everyone. Thank you for attending today's session, everyone. So we'll see you next Thursday, 31st of July.